Good afternoon and welcome to the ESAB Specialty Alloys live event. My name is Clemente Talarico, and with me as the presenters we have Mr. Peter Stones as well as Mr. Per-Åke Björnstedt for technical support. I'm pleased to announce here the 8th presentation of ESAB Specialty Alloys, which will happen every third Friday of the month at 14:30 European time via Team Live Events. The 8th presentation of the program will be the one starting in a few seconds with the title, What do you know about welding cryogenic materials? We will be very happy to answer your questions at the end of the presentation, which you can type in the Q&A box you will find on the top right of your screen. We intend to present on about 30 minutes and take 10 to 15 minutes more for answering your questions. And with that said, now let us start with the show with Peter presenting. Enjoy.
Thank you, Clemente. Good afternoon, everyone. And thank you for joining this, the 8th presentation. As Clemente said, we intend to talk for about 30 minutes, so there's an awful lot of information included in here, and it's really not necessary to take notes. If you see something that you like, you want more information on, then both Clemente's and my contact details are available at the end of the presentation. Please feel free to either call or email and request a copy of the slides. And if you think of some questions that you can't think of in the next 30 minutes, then again, please, by all means, just drop us an email. No problem at all. So we want to talk about cryogenics. It's a funny word, becoming more and more prevalent these days. So what does cryogenics mean? So I've just listed there the listing out of the Encyclopedia Britannica. Cryogenics, production and application of low temperature phenomena. So cryogenic temperature range is defined as being from minus 150 C, and it goes right down to absolute zero. You can't get colder than minus 273 Z. That's the kind of temperatures we're talking about. And what I want to do around the topic is present what are cryogenic applications. Why do we need to operate in temperatures so cold? Very specifically, what properties do the metals, not just the filler metals, but the base metals, need to have for applications that are so cold? What is it? What's the difference between ordinary base metals, ordinary filler metals that make the cryogenic ones so special? What are the grades? And obviously, we're a welding company, so we will talk about welding. There are some useful pointers to be taken into consideration whenever you start welding for these applications. So specifically cryogenic applications, we're talking about the temperature of liquid oxygen. That's really when things start. That's what we said, from minus 150 to minus 273. The coldest element that we're dealing with is liquid helium, which is down to minus 269. Minus 269 is a particular set of problems. You can't get much colder, and testing, for example, at those kind of temperatures is quite difficult and not too common. Why are we always talking about liquid gases? That seems a strange contradiction in terms. We're talking about a liquid gas. Why do we liquefy gas? And the reason is very simple. It's for volume. The volume of an oxygen gas is very, very much bigger than the volume the volume of liquid oxygen. So that's why we convert the gases into liquids. It's to make it easier to store and transport. And the applications that we're using for, not surprisingly, frozen food. LNG, natural gas, liquefied natural gas, is one of the biggest applications in the world, really, for cryogenics, and that's purely the size of the business at the moment. Obviously, MRI type machines require a lot of refrigeration. Rocket fuel is particularly special, and what's becoming more and more prevalent these days is hydrogen power. the technology is really starting to come into its own, and we'll talk about that later. So down to minus 100 C, we can see we're talking about ethylene temperatures. Then, or rather, I'll start at the top end. At 0, then carbon steels and fine grain 2% nickel steels are absolutely fine. So we wouldn't class them as being cryogenic. When you're getting down towards minus 100, then we need something a little bit more exotic, so something that, with a little bit more nickel in it, basically, to hold everything together. So the base material that's typically used down to minus 100 is something like a 3.5% nickel steel. When you get down to beyond minus 100, and we're talking liquid natural gas, then it's very typical to use 9% nickel steel. So that's got its own particular methods of production. It's got its own particular requirements for welding. Beyond that, there is life beyond LNG temperatures, and again, it's the four biggies: oxygen, nitrogen, hydrogen, and helium. Here, you need something better than a 9% nickel steel. So we need to be talking about austenitics or these INVAR materials, which are 36% nickel, aluminium alloys even. So as I said, what represents the largest in terms of volume, the largest market in terms of volume, numbers of tons of base material and filler metal materials, it's really in LNG. Because these are the type of storage vessels that need to be produced for storage and transportation. So the technology really has been based around LNG production. So utilizing low temperature mechanical properties, then something that always needs to be taken into consideration is this phenomenon called ductile to brittle transmission temperature, DBTT. It's a phenomena that's observed in most metals, and as a design engineer and as a welding engineer, then you need to be aware of this phenomena. Basically, what it's saying is that at room temperatures, then what could be perfectly acceptable with a nice ductile structure, once you start to cool it down, so as the temperature is reduced, then it goes through this transition from being ductile to being very brittle. And depending upon the grade, the alloy that's in question, the temperatures obviously change, and the steepness of the curve changes. So that means that it becomes brittle quicker, slower, whatever. So what could be very happy working in the UK would be completely unsafe working in north of Norway, for example. It's as simple as that. All ferrous metals, apart from austenitics, exhibit this transition temperature. However, nickel, because of the way that on a microscopic scale, the way that nickel is made up, that nickel-based alloys don't present this transition temperature. This is the reason why. In previous talks, I've gone into detail on the composition of nickel alloys and the reasons why they exhibit the mechanical properties that they do. So based on their composition, the way that they're made, then they don't exhibit this ductile to brittle transition temperature. That's why they're used. Obviously, as the base material for an LNG tank, it needs to be ductile and crack resistant, and that's why we're using things like stainless steel, aluminium, and nickel steel. Obviously, depending on the size, determines the thickness, the relevant tensile strengths, means how much volume of base material is needed. And one other point, that the LNG is it's at minus 163. It's liquid at minus 163 centigrade. So typically it's stored at minus 170. So there's a little bit of a safety measure there. However, when specifying the base materials and the filler metals, we specify them with properties at minus 196. So the reason being that that's a very typical, common temperature at which test laboratories can operate, and it's because it's the temperature of liquid nitrogen. So we're using liquid nitrogen to basically test for LNG fabrication. So if we know that the properties of the filler metals and the base metals are all right at minus 196, then to handle minus 170 should be no problem at all, and that's what they do. So the idea of using the 9% nickel steel is it's a low temperature, economical low temperature alternative compared to something like a 304L stainless. Because it's high strength, then you can reduce the thickness of the walls in the tanks. It's got enough strength to support. 9% nickel can be welded without brittle fracture. It's a low alloy content, like we said, so it's economical compared to 304L, for example. It is readily weldable. It's not susceptible to cracking, and it shows little deterioration of post-welding properties. Preheat and post-heat treatment not normally required at these kind of plate thicknesses. One thing in particular, provided low hydrogen consumables are used. One thing to watch out for that's not common, so someone operating in this kind of environment for the first time, this needs to be taken into consideration. Magnetism, it can be a problem. Handling and moving these plates around, you've a great risk of increasing the magnetism within the base material. If it's not possible to demagnetize, if there's a magnetic flux density in the steel, then that can cause all kinds of problems when welding, specifically arc blow. The arc goes where it wants. So what we would recommend is a flux density below 20 Gauss. If it's above that and it's not able to be demagnetized, then AC welding would be recommended. So in terms of welding solution, the little tips and tricks, what needs to be taken into consideration with nickel-based alloys is that they are usually very, very low in ferrite or even zero ferrite. And what ferrite does in there, if you remember, we call them austenitic stainless steels, like a 304L or a 316L. We call them austenitics, but they're not super austenitic. They're austenitic, meaning that they do contain some ferrite. The nickel alloys are in the super austenitic region, which means they have very little ferrite. What ferrite does is absorb some of any impurities that are within the steel. So you can have a very pure, very high quality filler metal, but the base metal, there may be some kind of impurities in there, and it's usually either phosphorus or sulfur. Sorry. When you're welding and you're diluting, you're diluting the sulfur goes into the weld metal. You're actually changing the solidification temperature of that part of the metal, of that part of the weld. Basically, whilst you're welding, the strength of the weld is not sufficient to hold it together, and then you get these kind of phenomenon, hot cracks, right down the center of the weld. So without having sulfur in there, then any kind of impurities can cause a lot of problems. And also what we should realize is the microstructure of these nickel alloys. They have very, very large grain sizes compared to other steels. So the large grain size means they've got very few grain boundaries, and it's the grain boundaries, explained in a very simple fashion, It's the grain boundaries that lock together that create the strength within the microstructure. Grain boundaries lock together, they bump into one another, they tie together, and that's what creates the strength. With the nickel alloys, they've got very big grains, so very few grain boundaries in comparison. So any impurities in here have a very large impact, a much larger impact on the weld metal than, say, in a 316. So that has to be, you have to be careful with that. Again, we're talking specifically for 9% nickel steel. We're talking LNG. We will go on to talk about other metals, other grades further on down the presentation, but we're talking now specifically for the 9% nickel steel. So a matching 9% nickel filler weld metal is not suitable because of dilution. You wouldn't get the strength. It would need heat treating to enable it to be used. So obviously the weld metal's got to match at least the strength of the steel, as well as have good ductility at -170. So it is not really only the nickel-based consumables that can do that, that have got that strength, that integrity at that low temperature. One other plus point for the nickel-based consumables is they put an austenitic weld metal down. So again, there's reduced risk of hydrogen cracking, whereas we're increasing the risk of hot cracking. There's a reduced risk of hydrogen cracking because it's austenitic and not ferritic. Basic SMAW and submerged arc fluxes will give a clean deposit in this 9% steel. In terms of the requirements, the specifications, requirements, then in terms of ASME, the requirements are for a yield strength of 690 pascals. And the project spec that we see typically is 70 joules, either 50 or 70 joules at -196. So which alloys are used for these 9% nickels? The main ones by far are either nickel chrome moly 3, nickel chrome moly 4, so alloy 625 or alloy C276. These are the ones, the two grades that have been used extensively over the years. We've certainly got lots of experience, and we've got literally hundreds of installations using either the nickel chrome moly 3 or the nickel chrome moly 4. The prevalence really of 625 nickel chrome moly 3 is that it's really a commodity. So there's a lot of people manufacturing this grade at the moment, so it tends to be cheaper. It's more readily available than the C276, but whichever is absolutely fine. In terms of the tips and tricks for welding, the techniques to use, we would say absolutely use a filler metal. If you're welding nickel-based alloys, always use a filler metal. Don't do autogenous welds without a preheat and without post-weld heat treatment. Again, something that we tend to say an awful lot of the time is keep the heat input low. We always say that with stainless steels, with duplexers, and with nickels. Keep the heat input as low as possible, and typically using a maximum of 1.5 kilojoules. We've mentioned it before, so it needs saying again. If magnetism is high, when we said that the level is around about 20 Gauss, use AC welding. This little diagram here is explaining the need to use a convex weld bead rather than concave. So if it was a butt weld, then we'd rather see more weld metal on the surface rather than a flat weld or a concave for a fillet. The idea being that you need some metal in there, you need sufficient metal in there to hold everything together. This really, it won't have the strength to hold everything together as it starts to cool down. That's when you start to see some cracking. Obviously, part of that is a good fit up. If you have lots of residual stress in here, at the fit up, then these alloys don't lend themselves to holding everything together without problems. So keep residual stresses low and use a convex weld bead. Stringer beads, rather than weaving, really to reduce the heat input. The less time that you spend in weaving, the better. So stringer beads, more runs of stringer beads rather than one big weaved bead. That means you're putting less heat into it, and we're trying to keep the heat input low. Avoid dwell, we said here, and backfill craters. Yeah, you don't want holes in there. You don't want a crater. There's no strength in that. You need the weld metal to keep it together. And again, something that we've said before about stainlesses and duplexes, and it's very relevant for the nickel-based alloys, is joint preparation. So before you even start welding, then it's essential to design the joint such that it has wider root gaps. As a rule of thumb, generally, the more highly alloyed the filler metal is, then the less it wants to flow. So the fluidity of the weld pool is not very good. It doesn't want to flow. So in order to ensure that you're getting flow and full joint penetration, full sidewall fusion through the joint has to be a little bit wider than you would normally expect for something like, say, a carbon steel. So the root gap needs to be wider and the angles need to be more open, whether it's a V, whether it's a J. And again, there are tables that we have to illustrate that. Again, dwelling on LNG, ESAB have produced this solutions handbook. So this is very specifically a complete portfolio of everything to do with fabricating LNG storage tanks. Such that we've got diagrams, representations of storage tanks, and every joint has its welding process, a recommended welding process, a recommended filler material at every stage. There's 43 pages in that. It is downloadable from the ESAB website if that's something that you're interested in. But like I say, please drop me a line if you can't find it, and I'll gladly help. So we've talked about LNG ad nauseum, but there are, as we mentioned, there are the 4 other gases that operate at temperatures below 196. So the material of choice for this is different. Hydrogen is the one that's coming into play more and more often. And what I've done here is I've just copied a page of the Gov.uk website. So UK hydrogen, this is just the UK hydrogen strategy. This is big numbers. 5 gigawatts of low carbon hydrogen produced by 2030. So if you take it into context that Sellafield, the nuclear power station that's been refurbished, the new reactor being put in there, is to produce 3 gigawatts. And the government are setting its stall out to make 5 gigawatts in basically the next 9 years. It's a phenomenal number. It's huge. So obviously the hydrogen has to be produced, and it has to be produced in the UK. We're not going to transport this thousands of miles. So the hydrogen has to be produced and it has to be transported, and then it obviously has to be delivered door to door, as it were. So this is a phenomenal business that is taking off in a very, very big way, certainly in the UK. TWI have a number of projects that are working on hydrogen. The colours of hydrogen, depending on how the hydrogen is produced, determines whether it's a green hydrogen or a black hydrogen. So you produce hydrogen by sustainable means. So if you're using solar farms, wind farms, wave power, then that would be green hydrogen. And at the other end of the scale, you can produce hydrogen using nuclear power, which seems a bit strange. But again, the TWI are taking it on board in a very big way. It's going to be some very big projects coming up. If you have £54,000, then you can buy this hydrogen powered car, which would be fine if you had one of these next door, which is a hydrogen refueling station. So the way that this works is the car obviously has a hydrogen tank. You fill it up with liquid hydrogen. The fuel cell basically produces electrical energy, and its byproducts is essentially water. This is why it's so nice and clean, and it's going to come on board in a very big way very soon. And then you've got an electric car. So rather than using a battery, you're using a fuel cell that converts hydrogen into electrical energy. And these are available now. You can buy one of these if you're in the right place. So again, these things are going increasingly popular. And this thing is a off-the-grid electric vehicle charging station. So this is essentially what we saw in the car, in the vehicle. It's a hydrogen tank with a fuel cell that's converted, that's producing electricity. So the idea being that this thing doesn't need to be plugged into the national grid. It doesn't need to go into the mains. It's powered by hydrogen and producing electricity specifically to charge electric cars. So these can be deposited anywhere, like in the middle of the desert, the jungle, whatever. So it's making the potential utilization of electric vehicles a lot more real, a lot more accessible than today. It's difficult enough driving from John O'Groats to Land's End in an electric vehicle. You have to plan it out. These things are going to be becoming more and more popular. So the materials that we're talking about here, we're talking about austenitic stainless steels predominantly. So this is the same chart we saw before that had the LNG at 9% nickel steels. So for the nitrogen, hydrogen, helium, then we need something like an austenitic stainless steel, the 36% nickel, an Invar, or some aluminium alloys. So two grades that we have that I particularly want to mention because they're quite special. So we have a 1912 3L cryo. So it's a 316L, but it has a much lower ferrite than a typical 316L. The ferrite is normally 2 to 5, is between 2 and 5, I should say, but normally it's 3. So with a ferrite number of 3, this means that it's usable down to minus 269. The Charpy value, the impact toughness at minus 196 is 70 joules. So these is certainly one of the materials of choice for hydrogen tanks. The other grade that I want to specifically mention is this 308. We've got a 308L grade. Again, it's got at minus 196, it's 75 joules, so it's even better than the 316. However, this has got is tested, it's approved. We've got approvals on this for minus 269. We've got a toughness value of 40 joules. So it's a practical application. It's a practical solution, I should say, for hydrogen tank applications. So it's currently in use. It's becoming more and more prevalent. And really, to finish off, I just want to list or go through the portfolio that we have. All of these grades, and I don't propose reading them out, but obviously we've got MIG, we've got TIG, we've got submerged arc, we've got flux core, everything, every welding option. And all of these are being used for cryogenic application somewhere. Okay, so we've got a huge range of this. Flux core, I mentioned, submerged arc with fluxes as well. So thank you very much. I think my 30 minutes is up. Thanks for your time. You can see Clemente and myself have our contact details there. Please feel free to get in touch with us if you think of something later. And the one other thing I just would mention is the next presentation is on basically the importance of consistent quality of filler wire, and we'll introduce the ESAB robust feed as well, and that's on the third Friday of November, which is Friday the 19th. So thanks very much. Clemente.
Thank you, Peter. Well received. As well, thank you all of you for the participation and the good questions highlighted. So I will start with the first question that we have, and the first question is, why are the nickel alloys prone to centerline crackings? Peter, Parocchi, what are you saying on that question?
Parocchi, do you want that one?
Go ahead. You have already explained that one, so in a very good way. So go ahead.
Because of the grain size of the nickel alloys, as I mentioned, the grain size is very big, and the grain boundaries, the number of grain boundaries is very small. So in terms of strength and toughness in liquid solution, these don't want to hold together, and they're very prone to impurities. Impurities would generally come from your base metal. So any traces of phosphorus and sulfur affect the microstructure even worse, and it changes the solidification temperature. So you have areas that basically don't solidify. They don't solidify quick enough to hold the weld together. Does that explain it? Parocchi, you got anything else?
Good enough, sir.
Okay.
Good. And I come to the next question that we have. Where can I get the copy of the LNG solution handbook?
I believe it's available. I thought it was available on the ESAB website. If anybody's having any trouble, please drop me an email and I can sort it out.
Good, fantastic. I come to the third question, and it seems that this is the last question that we got. So in total, we got only 3 questions. So it seems that you were very clear, or
sorry, you have 3 more questions, 4 now.
Yeah.
So
right.
go ahead.
Okay, good. Okay, now I see it. Yes, that's right. I have this one here. What are the approval for Exoton Cryogenic 99L?
That's for you, Parocchi.
Yeah, sure. We have TÜV approvals for both of them. But for TIG, we have a quite unique approval down to -269, actually. It's a TÜV approval. And we also have a DB approval.
Okay, good. Thank you very much. So now it starts to become more interesting because we get more questions. So, do you recommend specific ferrite numbers of austenitic welds under cryogenic applications?
I would say that you should be, I mean, a typical number would be around 5, 6. We recommend up to maximum 8 for this type of alloys. But for example, 99L, we are around 5, 6, 7. And for the 316L, as Peter pointed out earlier, we actually have an average so far around 2.4, 2.5, around there, 3. Yeah. So that is the range we see as fits the purpose best.
Very good. Thank you very much for that. I have the next question for the Exoton 316, means the 1912-3Al cryo, used for -269 degrees C. Does it ensure lateral expansion above 0.38 millimeters?
Yes, we have done tests showing that we fulfill that. And also we have shown that as extra information to this, we are above 40 joules as well at this temperature.
All right, thank you very much. The next questions, I will go quite quickly so we can hold the time as well. Did you characterize hydrogen embrittlement resistance with 308Al or 316Al welds? What is the best choice? What is the best choice between 308 and 316Al welds?
I don't think we have done that investigation. I don't recognize that.
Anyway. You're talking specifically in terms of hydrogen embrittlement?
Yes.
No, we have to look that up. I haven't seen an investigation so far.
No, I don't recall ever being asked for low hydrogen grades, to be honest. You know, we do a low hydrogen super duplex, for example, but I've never come across anyone asking for a low hydrogen either 308L or a 316L. So sorry.
Maybe they're referring to covered electrodes, but we need to come back on that one. If it is covered electrodes they are referring to.
Yeah, please, whoever asked that question, please drop us an email and we'll investigate and get back to you.
I have another question here. Which solution can be used to do the Charpy test at minus 269 degrees C? So which solution?
Go ahead, Peter, show the slide.
Yeah, it has to be liquid helium.
Yeah,
it's the only thing that's at that temperature. So you have to find a laboratory that can handle liquid helium. Essentially, that's the thing. It's not so common, as I said.
Yeah, exactly. And it's only a couple of laboratories here in Europe that can actually do these tests. And also, when you do the test and take out the sample, it will quickly be warmer than this minus 268.9.
Yeah,
so that is the tricky part also.
You have to freeze everything. You have to freeze every part of your equipment that it touches, and freeze the environment. And yeah, it's tricky and it's expensive.
All right, and I think we are coming to the last question. And the last question is, explain about the basicity in submerged arc welding fluxes.
It's not my forte. Barocca?
I'm not sure I understand the question, to be honest.
So the question is explain about...
What is basicity?
Yes, exactly. Let's start with that.
I mean, the lower you are in basicity in the flux, the higher the impact strength normally is.
Good. And how I can get the lower basicity in the flux?
How do you get the lower basicity?
Yes.
Oh. What is influencing the lower basicity?
Exactly. I don't remember the elements that are included in the. We should have my colleague here explaining this. You have to come back on that as well. I don't remember the elements that is important here. Yeah,
it is at the end. It is the elements that you have in the flux,
yes,
which
absolutely.
is supporting the basicity. And
like baking a cake, it's a recipe.
Yes, exactly.
And alters the flavor.
Exactly, and then lower the basicity, higher the impact strength. But at the same time, it's also not so easy to weld. Or let's say if the basicity is lower than it is different than if you have a higher basicity during the welding process and the slag removal and the slag building and so on. So that has something.
And normally the slag removal is more difficult with higher basicity.
Exactly. Good. All right. So please note down Peter's and my contact details from the screen. we are already now very happy to answer further questions and give some more clarification to your question that you have brought up. With that said, we wish you a successful rest of the day and see you soon in the next live event in 1 month. Thank you very much.
Thank you very much.
Thank you. Bye.